Okay, good afternoon, everyone, or good evening, good morning, depending on where you're located. It gives us great pleasure to introduce our second Industry Insights keynote. We have Dr. Arpan from TCS Research. He's the Chief Scientist and Research Area Head of Embedded Devices and Intelligent Systems. And he's currently working on connected health, smart manufacturing, and remote sensing, but he's done so many different areas over his last 29 years of working there in industry. He's on the editorial board of many journals, and he's submitted like 160 plus patents, of which about 80 plus have been granted, and published about 140 plus papers. He told me earlier that very important for everybody in the room, TCS is actively hiring, especially his group. They're looking for pre-docs, postdocs, interns, and full-time hires. So if any of you are interested, please contact Dr. Pal later. He's going to give us a fascinating talk on his own insights on the future of communication. So without any further ado, Dr. Pal, please.
Thank you, Rajesh. Thank you for your kind introduction, and thanks for giving me the opportunity here for giving this talk. So let me share my screen first, and then. So I hope my screen is visible.
Yes, it is.
Okay, thanks. So what I'll do, I'll just try to walk you through, even though the topic is very generic, insights and future of communication, market and technology trends. But I think what I will do is like our experience, that what we are seeing in this and where it is moving, and the areas that we are working in, where we see the things are moving around. So I'll just try to give a glimpse of that. So in more of experience sharing than the kind of a talk that is there. So effectively, if we see the key, what is as a telco customer, customers, what do we see in this new 5G network? What are the key business and technology trends? So I'm kind of listed it out, so I'm not going to read them out. It is understood. But effectively, if you see on the business side, there are some key trends are emerging, which is a private 5G, then hyperscalers as a service. These are coming, and also I think both the geopolitical issues and the COVID-19 actually kind of had a lot of effect in the 5G on the business side of it. On the technology side, you see that these are all known: network disaggregation, OSS, you mentioned, all those things are coming. But this non-terrestrial networking, edge computing, these are also coming up, and it has to kind of coexist with the existing governance system too. And there are some next-gen technologies, which is the millimetric wave, HPC, metamaterial, quantum, many other things are actually coming in that space. And I'll try to touch base of these things as I go forward in my talk, and the kind of research we are doing in TCS in that area. But before that, again, that if we take look at the market part of it, so there are three key market trends that are coming in the communication market. So first is similar to IT, the network workloads are moving to clouds. So this is a very key trend, and there's a large market that's going to emerge from there. And there are all these NFB, NFVIs, MEC, all these technologies are going to become important along with the private cloud to do this. Second key trend is the softwareization, that is increased focus on network automation and orchestration. So network as a service, and it's going to become very important, and AI is going to play a key role in this. And this also is a very large market, as you see here. And the third thing is very kind of pandemic specific, but there is a rebound on the 5G investment post-pandemic. Even though we cannot get it post-pandemic, we are still amidst that next wave, but still it is going to end very soon. And this, so 5G infrastructure is actually scaling up like anything. And even if you, so that is a very encouraging thing to look at. So I am going to talk about very detailed some of the use cases. So I'm not going to talk, this is a more of a slide just to collect this information. I think even in this slide, we can talk about 15, 20 minutes. I'm not going to do that. But effectively what it means that every vertical today, we are going to have applications that will need this kind of 5G kind of technology to take it forward. So be it manufacturing or retail or healthcare or even government, banking, agriculture, everywhere. So I'm not going to go details on any of these use cases. So some of them will cover today in my talk. Rest of the thing, maybe something is there, some question I can take it later. But in the interest of time, I will not cover the details of each of these. But these are all the use cases that we are saying that our customers are asking from us, and across these different verticals. And each of them will need I would call not a quote unquote 5G, but a very, I would call high throughput, low latency communication system. Without this, we cannot deliver. And on the horizontal technology front, these are the 5 areas which we think that is going to come in. So private 5G, I already mentioned, WAN on 5G, and then the Wi-Fi 6 and 5G together is an enterprise case, is a very important thing. And I think there was a panel discussion yesterday when one of my colleagues, Hemant, actually talked about this thing. We know that security is also important. And the age over 5G is going to be, I marked it because this is something I'm going to cover slightly in detail also, that how exactly we go about it. Okay. So now with that background, so let me kind of give a outline of how exactly this edge is coming in, that why we need intelligence at edge, and how do we need to move beyond telecom edge, move toward device edge. So effectively, if you see the edge thing, that requirement, there are 4 key clear requirements are coming. These 4 bubbles I have given. So first requirement is a low latency from the network, because of any application that is having a real-time sensing and control. And I've given a picture of a drone here, but any kind of drone or a robotic system or many of the manufacturing systems, they will have this real-time sensing and control as a requirement. So think of a plant that it is sensing something, and then based on the sensing that it has to actually, maybe it senses something wrong and it has to stop the operation, or you have to do something. So effectively, the low latency is becoming a requirement in most of the scenarios where this is required. It's not only about the telerobotics and telesurgery, which typically we talk about, but many of the enterprise applications need this. Only the latency level changes. What you define as low is actually different for different applications. The second thing that we are saying is also that many of the applications, intelligent applications today, depend on multiple sensors, analysis or creating AI inference based on multiple sensor data. And usually this sensor data needs to be captured and analyzed synchronously in many cases. And so that synchronous acquisition, multi-sensor fusion, sometimes when you have a sensor array and all, they also need some local processing, and you may not be able to actually always go back to the cloud to do it. Okay. So that, and the third scenario is this reduced data requirement, that usually it kind of comes with this, that know that it is always there. So you have to save the battery power. All these devices that you are having in the edge today, they are all battery powered. So always you have to save the battery power. And we know that communication always takes up the maximum battery power, more than the compute. But still you have to conserve the bandwidth because of various reasons. Either you are not scaled to, that the bandwidth is not good enough, or even if it is there, there's a cost associated to it. And also you have to ensure the reliability. That if I have to going back to the cloud to do something and getting back the data again, how do we really make it in a very reliable way? How the network is underlying network can be reliable. So that is another requirement. And fourth requirement is a very, very industry specific, but we are seeing more and more this from the customer. I have given some pictures. So is the privacy, which is basically coming from the data visibility and regulatory concerns. So it is not only privacy, I'd call privacy, security, all this together. And I've given 2 pictures. One is part of the, you can understand the healthcare. Obviously, there is a need to actually keep the data in the local edge or local device and not send it out, because that is only way we can ensure the privacy. So which means the intelligence and the AI has to happen on the edge. The other industries also are coming some, yes, I'll give a simple small example is this airline industry. So airline industry, there are different kind of regulatory concerns for which they think that 5G in an airport and other, it may not be possible. So there is some concern about it. So then how do we actually send that create a connectivity there? So there will be such regulatory concerns will come, and some cases these privacy concerns will come, which will actually force our data to be locally inferred. And when we do that, this edge computing angle, if you see the different applications, there's a very nice Gartner report that came out a couple of years back, which kind of give this very nice view of this 3 area angle of business, people, and thing. And then if you think about it, that intersection of things and people are the robotics, the collaborative robotics part. The intersection of business and people is the AR, VR, XR, or the metaverse, we call it, and as we are calling now. And the intersection of things and business is the IoT. So all IoT, AR, VR, XR, and the robotics application typically are device heavy, and these devices have compute power. The challenge is that how much of this intelligence we bring in on the device, and how much of the intelligence we want to bring it back to the cloud. And that is the challenge that we are going to. Everybody is facing that problem. And just to give some example of application use cases. So this is one of our use case that we actually worked on. Our customer is one of the large car seat manufacturer in the world actually, and they're very, very finicky about their car quality, and they want a vision based detection as the seat gets manufactured and goes through the assembly line. In real time, they want to detect any wrinkle that is getting created in this car seat. And the challenge is that you not only have to detect, you have to immediately understand that, because so that they can adjust the process. So the next seat that gets, maybe some tension is not right because of that the wrinkle is coming. So they will adjust that before the next seat gets manufactured. So that is a kind of a complete end-to-end closed loop intelligence that is residing. But the challenge is, you see that the model size is huge to create this kind of the AI model that you usually use, deep learning models to detect this. We can get very good accuracy, but they're very, very large size. But how do we do? But we need to do real-time inferencing near the edge, but which do not have that kind of a compute power, and offloading to cloud is difficult. So I'm just giving the example. I'm not telling that how we are solving these problems using edge, but I'm telling that problems where actually we are saying that offloading to cloud is not the only option. It has to be an option that something local versus the cloud offloading together has to come up. This is one example. This is a second example, very interesting example of this is a laparoscopic surgery that happens. And this is a real data from our career part that, what is happening. This is actually the laparoscopic tool, which is kind of surgery. When they do and they cauterize the cells, there is a smoke that comes out. And this smoke in a very occluded small area inside the body cavity, it actually occludes the vision of the surgeon. So it's a real problem. And the problem that they came to us was to tell that, can we remove this smoke? And we can actually do this we use some GAN-based synthetic smoke generator to train a model, and through that actually you could remove. You can see that the reconstructed in the top right is much, much cleaner view than the smoky view that is coming in the middle compared to the. But the challenge is, now think of this tool. This is happening it is operating on the operating table. And I have this tool. So effectively, in real time, I have to actually do this analysis. And so I have to run this deep learning model and remove this smoke and give this output in real time into the surgeon, so that surgeon can actually see the reconstructed desmoked version, not the smoky version. And if using that, they will do the surgery. So I'm just giving the example again, that how important is this, and how will it be always possible that we go back to the cloud, get this done, and come back? And can we do it reliably? Always there's a problem. So there may be a need to do again inferencing at the edge of device edge of this. Maybe on the tool that it is operating, you have to attach a small computer there to do this possibly in the OT. The third use case we are talking, these are very closely, we are working with this concept called teledrive, where it is a telepresence application, where actually this is becoming a very important in the new era after the post-pandemic, that that is something like your robot becomes your avatar. Like today I'm giving a talk from behind. Maybe there could have been a robot which was there in the stage, which is the avatar of me, and I could have navigated that robot sitting from away. Okay, so the point is that it is a teledrive. That's why we call it teledrive, as you see here. So effectively, if you say that there is a person who is actually driving it within an office or within and this robot actually carries the face of the person who is driving it, and the other side can directly interact with them. And so this multimedia chat, collaborative multi-presence, and this auto, semi-auto floor mapping and navigation, and there's augmented reality part. So these are all together, the application is coming. And as you understand, so how do we really now? So the underlying network has to be reliable now to do it, and we have to actually resort to quite a bit of protocols tweaking. to make sure that we actually can get it in the real time. The second use case, this is something we are very recently done, and it is beyond telepresence, is a teleoperation over 5G, which we actually did in collaboration with Airtel and DOT. And effectively, what it means is that a robot actually could be operated remotely using some AR/VR headset, and they in the actual place the robot will be able to do some applications, the actions actually, and you can see those actions that is there. It is a hip stem implant casting process that is what's taken that as a. So there's a pickup, there's a dipping, there's a drying, and there are all these tasks that robot is supposed to do. But it is completely operated by an operator who is sitting maybe 1,000 kilometer or 2,000 kilometer away, and still they will be able to do it. And that was the challenge that was there, but we could do some pilot now, and it seems to be working. And this is the network architecture of that. So if you see that one side you have got the teleoperator robot, but they have the robot arm and the mobile base and streaming server, which are all connected to a network, either a 4G. We have created both 4G system and also connected to the 5G test beds also. And then it connects to the cloud. And on the other side, the operator also wears the VR headset, and it has the VR controllers, and then it also connects to the cloud. And it has to now seamlessly operate. And it was extremely challenging. So it is a real low latency, high data throughput use case. And how we could manage it. And the good part was that we did that thing. So we did both with the 4G Wi-Fi first, and then also the real 5G test bank that the Airtel gave that. And very recently, I think just last week, this press release came that Airtel TCS successfully test neural manufacturing on 5G network. So this is actually now happening, and we actually demonstrated in the Airtel 5G lab in Manesar. But I'll just want you to look at this comparison in this here. So there are multiple locations. The operator and the robot was kind of always distributed. But the main point you have to see that what the plot shows is that robotic arms accuracy intended versus what the operator actually wanted to do, plus where actually it went. Because it's a closed loop control system. The more is the latency, the more difficult it becomes to control. Okay, and it clearly shows that if you see the variation, the 5G and between 5G and 4G, the variation, the standard deviation actually is coming down by more than double. We have almost a centimeter level accuracy now there. So that is the value. So which was not possible using 4G. So just give the example that how important is that network latency is in this kind of closed loop real time control systems. Okay, so the beyond 4, then I'll just kind of spend the next kind of few minutes and then close that beyond 5G and towards 6G, the next generation technology is what we are. So what I told you is what we are doing now. But I'll just give a glimpse of the research that we are trying to look at in the next generation future. And as we know that obviously that from 5G towards 6G, that there is a lot of areas of improvement that the spider chart shows. But one area of improvement that we have, two areas I would say is going to become very important. One is this meta surface based lenses. So you can use this metamaterial based surfaces, which can actually operate as a kind of a lens or a radome in front of your normal antenna that antenna fades. But what it can allow you to do it can actually have a very narrow multiple beams formed with using very small size lightweight antennas, not very large, because usually for a large beam you need to go for large antennas. So this meta surface allows us to do that. We are already creating this metamaterial based systems to really do that. And the extension of that in future will be this meta intelligent reflecting surfaces. So the meta surface antenna will make sure that we actually have a very narrow beam with very high QoS for a targeted kind of a connect user you need to connect to. But if you want to do it more general way, you want to improve the coverage, then we are trying to go for these meta intelligent surfaces, where actually because it's metal material, the meta surface is nothing but a regular metals printed in some pattern. And then controlling those patterns, switching them on and off, you can actually control how the wave actually propagates. The only thing you have to make sure that these patterns dimensions are actually in the kind of in the similar order of the wavelength of the thing. So lambda kind of a thing. If that is there, you can control this. So using this, you can actually also create this. Suppose think of this, you can actually put some part of the area is not getting a good signal. You can just put a meta surface reflector and actually programmatically control that. You can actually get that area that it actually goes to the and get the good signal strength. So this is the second thing that is coming in. That is a big thing about metamaterial and meta surfaces coming in. The second thing that is coming, that I was telling, that effectively what I tried to harp on this is actually the need of a local compute, and because there's a limited network, there is also need for the offload compute. And we need to kind of define this seamless fusion of devices, network edge, and cloud. And looking at an AI inferencing perspective and AI-based learning perspective, how do we do it? So that has to become a more of a standard part of the event, because this year the network and the compute are actually going to come together, because this will become a network aware partitioning of between edge, network edge, and the cloud. So how do we do it? So that part has to come in as a thing, and then you can optimize that, whether you optimize the latency versus accuracy versus power. All this you can do. And all these applications of autonomous driving, drone fleet management, telesurgery, all will ultimately need this kind of, I would call, segmented fusion of devices, network edge, and cloud coming in a seamless way. And that is still to do, and we have to work towards that. And finally, the other thing that we are seeing as a trend is that this terahertz thing that is coming, and terahertz things that communication can be used as an imaging system. It can look inside your body, look inside the other things. But the interesting thing that we are seeing now is this joint sensing and communication. So can I use the signals that is sent by a millimetric wave transmitter that is available in the 5G system or 6G system, and use the reflected data out from there to create can I use that as a transmitted waveform from my radar, and I create a radar imaging system? Can I create a SLAM for my autonomous vehicle? So these are going to be the next thing that we are going to work on, and that is also we are seeing as a trend. And just to give a pointer, that we already found for kind of floated this RFP for a 5G test bench with all different application in health manufacturing, healthcare, and many other things. We got very good 7 institutes that presented proposal in all the IITs, and we are kind of in the shortlisting. But this we are very much excited, because you can see the use cases. All these use cases will be actually become a very nice demonstrator of 5G. And you saw one of them in the action in the telerobotics, the number. So in smart manufacturing, number 2. But all the other things also will actually be working with IITs and ISC and everywhere to make that open. So once we actually close this. So with that, I'll end. So some of my work that I actually covered came up in this IEEE newsletter, which kind of starts with the cognitive IoT and moving into kind of how do we use it for the manufacturing and healthcare, and then how actually a distributed architecture and tiny devices is going to become the future. And there are 2 books that are there. That one book is on the IoT, we did almost 5 years back, but very recently we also kind of with IIT Kharagpur collaborator, we wrote this book on digital twin and manufacturing, which actually covers many of these ideas that I was talking about. So with that, I will end. Thank you. Hope I am on time.
Thank you, Arpan. This is Amit, the TPC co-chair. Thank you, Arpan, for a wonderful talk. I will open the floor for questions. Anybody has questions? We have one there.
Hello, sir. I'm Mohammad Zishan from IT Patna. I just have a simple question, which you touched upon as well in your talk right now, that like we know that most of our state-of-the-art deep learning methods are getting bulkier by the day, and deploying them on edge-based devices is like getting difficult every time. Like every next state-of-the-art is getting more complex to actually implement it. So like how exactly do we approach this?
Yeah. So there's a very good question. Because of time, I could not cover it. So this is the core research actually. The point is that how do I take a large deep DL model? Suppose I have a DL model of, I'll give an example. We did this for a year, that there is a ECG analytics. You have to detect atrial fibrillation ECG. The DL model size was 10 MB. Okay. And I had a implantable or wearable kind of a ECG device where the memory was only 5 to 56 KB. So how do we kind of now in black box how can I take this model And without minimal kind of a reduction in performance, how can I now reduce the size? So there are multiple approaches. So I am just giving the name. So there is you can just take it. So there is a concept called network architecture search, NAS. There is a concept of what you call as the auto pruning. There is a very nice algorithm that has come out from MIT called lottery ticket hypothesis, LTH, which actually does a automatic pruning and gives the almost 10 times better performance than hand pruned network. And there is also a very powerful technique which we used for this ECG, where we actually reduced it from that 10 MB, we reduced it to 60 KB with almost 0.5, only 0.5% reduction in the accuracy. Is a concept called student-teacher network and knowledge distillation. So actually what you do, you make your DNN as your teacher network, and you have a very small student network, and using some knowledge distillation technique, you train that network. And basically you only take the important part of the DNN and put it part of the smaller network. And so it is a tedious affair, but once you do it, you can actually reduce a lot. So I can give those. These are 3 techniques you can use to really reduce the size.
Thanks, Arpan. One more question.
Yeah.
Thank you, sir, for the nice talk. I'm Dr. Rishikesh Venkatraman from IIIT Sri City. So towards the end of your talk, you touched upon digital twin for smart manufacturing.
Yeah.
I just wanted to know, like when we talk, we have sensors, sensing and communication of the information gathered by these sensors.
Yeah.
But when we are talking of digital twin for smart manufacturing, in terms of the technological challenges, do you expect more from the communications background, or do you expect more challenges in the data analytics space to analyze and then make a digital twin?
So you see there are 2 parts to it. So in the beginning, the digital twin, the challenges today are all compute challenges, because we don't even know how to build the twin and how to really create a twin that actually be using, which will add value to a customers or a users. Say if a plant is using it, how the twin is going to help effectively. There will be some what if analysis it will do, another thing. But more and more what we are seeing as we go forward, the digital twin will become a proxy for your decision making. Okay, so today it is done only for planning. So if you want for planning only, you don't need that communication part. It's not real time, actually, it's offline. But more and more as the twin will mature, we'll see that same data feed that is going to the plant, same data will be fed in the twin, and that output will be used to maybe take a prescriptive action on the plant. Like I was telling, suppose I'll detect some abnormality in the plant, the twin will tell me that this is extremely catastrophic, you have to immediately shut down the plant within 30 milliseconds. And then it has to come back. So once that comes in, then the communication becomes important in that also. That's the challenge. Okay.
Thank you.
But we are still not there. Yeah.
Thank you, Dr. Arpan. We have run out of time. As a token of our gratitude, we would like to, we can't give you anything physically, so we'd like to share a virtual coupon which will be sent to you in due course. So you should be able to see that on your screen right now.
Thank you.
So help yourself to something on Amazon. Thank you again, once again. And with this session ends.
Thank you.
And we'll move on to the next industry speaker. Thank you again.
Arpan. Thank you, Arpan, for a great talk.
Okay. Thanks, Rajesh.
Thank you. The next speaker is ready, so we can just go live. By the way, I just checked. Amit.